the arrow started at the pi bond, because that's where the electrons are. They bounced through carbon 2 to attack the hydrogen. This arrow is unambiguous. When we draw organic chemistry mechanisms, we use curved arrow notation to show the flow of electrons. Most of the time, the curved arrow notation is unambiguous about what it is representing. Curved arrows start at a place of high electron density, nucleophiles. They point to a place that lacks electron density, electrophiles, clearly showing which bonds are being formed and which bonds are being broken. This isn't a video on how to draw curved arrows or what they mean. I've got a link to that video down below. Instead, I want to focus on ambiguities in curved arrow notation and how we can solve that. But like I said, for most arrows, that is unambiguous. For an acid-base reaction, the base, a lone pair of electrons on the base, attacks the acidic hydrogen, forming a new bond between the base and the hydrogen. The bond between hydrogen and chlorine breaks. Those electrons go on to chlorine as a new lone pair, unambiguous. In an SN2 reaction, the carbon nucleophile attacks carbon number 3. There's a new bond formed between carbon 2 and carbon 3. The bond between 3 and bromine breaks. Those electrons go on to bromine as a new lone pair. Maybe you haven't gotten here in lecture yet. Don't worry about it. That's not really the point of this video. I have entire playlists on acid-base reactions and SN2 reactions that I'll link down below. When the nucleophile is such that the arrows start at a bond rather than a particular atom, there is a bit of ambiguity in a situation like this. When the electrons in the bond attack hydrogen, which atom is actually the one doing the attacking? Which atom uses those pi electrons to form a bond with hydrogen? Which atom is the nucleophilic atom? This arrow is ambiguous. We could form one of two possible products, either where carbon 1 was the nucleophile to form the bond with the hydrogen, or where carbon 2 was the nucleophile to form the bond with hydrogen. This arrow doesn't tell us which of these products is the one that will form. There are ways that we talk about this. We talk about the pi bond being like a gate, and it can either hinge through carbon 2 to form a bond with the hydrogen, or hinge through carbon 1 to form a bond with the hydrogen. And that's fine. And Markovnikov's rule tells us which product will form ultimately. I have a video about Markovnikov's rule below. But again, this is a video about bouncing arrows. This arrow is ambiguous. This arrow doesn't tell us which atom is the nucleophile, doesn't tell us which atom forms a bond with the hydrogen, and doesn't tell us which of these products is the one that will form preferentially. So if traditional curved arrows have an ambiguity built into them when the arrow starts at a bond, how do bouncing arrows help resolve that ambiguity? Before I tell you, let me just include a disclaimer here. I'm not your instructor. I'm not the one grading your exams. Maybe I am. Maybe you are one of my students. Hi. But I'm probably not the one grading your exams. You will need to talk to your instructor about how they will grade your exams, whether or not they will accept this bouncing arrow formalism. I think it's better. Hopefully you think it's better. If you do, talk to your instructor about it. If they don't agree that bouncing arrows are an acceptable way to draw curved arrows, maybe send them a link to this video. Have them watch this video. If you're an instructor watching it, hi, thanks for joining us. Here's the reason why I think bouncing arrows are less ambiguous, more practical, and better suited for organic chemistry. The traditional curved arrow has an ambiguity. Which atom is the one that attacks? Let me show you how the bouncing arrow resolves that ambiguity. Pi bonds are nucleophiles. We start the arrow at the pi bond. That's where the electrons are. I see in this product that it's carbon 2 forming the bond to hydrogen. So here's how we draw the arrow. We start the arrow at the pi bond, and the electrons springboard through carbon 2 on their way to attack that hydrogen. That builds up too much electron density around hydrogen, break the HCl bond, electrons onto chlorine. That part's the same. But notice the bouncing arrow. The arrow started at the pi bond, because that's where the electrons are. They bounced through carbon 2 to attack the hydrogen. This arrow is unambiguous. This arrow shows us that carbon number 2 is the one attacking the hydrogen. This arrow shows us that this is the product that must be formed from these arrows. Is it arbitrary? Yeah, I guess so. So were curved arrows the first time. Curved arrows are an arbitrary invention by humans to show how reactions occur. The electrons don't actually follow this path from the pi bond to the hydrogen. The molecules get close enough that the orbitals overlap and the reaction just occurs. There is no curved arrow pathway that the electrons take in the first place. So why not bouncing arrows that remove the ambiguity and show us exactly what is happening? Precision is important. Precision is key in organic chemistry. These bouncing arrows were developed by Suzanne Reuter at Virginia Commonwealth University back in 2009. We've got a link to the original JChemEd article down below if you'd like to see what she has to say about them. These bouncing arrows show us exactly what product is going to be formed. How could we draw the bouncing arrows to show this product being formed? Maybe go ahead and pause the video. See if, just from what I've shown you, if you can show the bouncing arrows that will form this product. So we know things about pi bonds. Pi bonds are still nucleophiles. We'll still start our arrow at the pi bond. That's where the excess electron density is. If we're going to form the hydrogen-carbon 1 bond, these electrons need to bounce through carbon 1 to attack the hydrogen. HCl bond breaks, electrons onto chlorine, that part's the same. And here we show unambiguously that carbon number 1 is the carbon that attacks the hydrogen to form the intermediate. These arrows are ambiguous. We talked about the hinging gate mechanism before. If you just looked at these arrows, it almost looks like the electrons are hinging through carbon number 2, and that, say, this product over here should be the next intermediate. That seems to be implied with the way this is drawn. But if you've gotten to alkene additions, then you know that's not true. The correct answer for the intermediate is this one, where it goes through carbocation stability, Markovnikov's rule. That's not the point of this video. I've got another video on carbocation stability. I'll link down below. But notice the ambiguity here almost leads you in the wrong direction just by the way it's drawn. The bouncing arrow removes all of that ambiguity. If the traditional curved arrow says that the pi bond is attacking, the bouncing arrow adds from here. I really like that. I didn't come up with that. My friend and mentor Rick Mullins did in his textbook. I've got a link to his textbook down below. His textbook talks about bouncing arrows. It uses bouncing arrows in the textbook and says that as the pi bond attacks, it attacks from here to form a bond with hydrogen to form the Markovnikov most stable carbocation intermediate. That's really useful. This is a really useful way of showing curved arrow notation that removes the ambiguity from traditional curved arrows. So I think bouncing arrows are a really important tool in organic chemistry, but they're not useful in every mechanism. They're really only useful when you have a bond as the origin of electron density in a nucleophile, a sigma bond nucleophile or a pi bond nucleophile. Got some examples listed here. The electrophilic addition that we just talked about. Unambiguously, the bond breaks. Carbon 1 attacks bromine, forms the bond between 1 and bromine. The bromine leaves as a leaving group, bites back down. We get the bromonium ion. I have a video about that below. Carbocation rearrangement. When the carbon-hydrogen bond breaks, hydrogen gets to keep those electrons and move over and form a new carbon-hydrogen bond with carbon number 3. Got a video about carbocation rearrangement below. And finally, electrophilic aromatic substitution. When we have to worry about ortho, meta, and para directors, maybe you don't know what those are yet, don't worry about it, you'll get there. Which director, where the new electrophile goes, is really important and can be ambiguous with traditional curved arrows. The bouncing arrow unambiguously shows that carbon 5 is attacking the nitrogen, and the new nitro group goes on carbon 5 in the meta position relative to the original nitro group. Bouncing arrows are a really practical, really unambiguous way of showing curved arrows. They're not useful in all situations. They're not useful in traditional bronzed acid, bronzed base situations. They're not useful in resonance. They're not useful when a lone pair is a nucleophile, like an SN2 reaction or a nucleophilic acyl substitution reaction. Again, if you don't know what those terms mean, don't worry about it right now. You'll get there. But this is where bouncing arrows are really helpful, when the origin of the electron density is a pi bond or a sigma bond. I use these in other situations as well. I use bouncing arrows in Grignard reactions, in organolithium reactions, in sodium borohydride, in lithium aluminum hydride reductions. These are all places where the arrow starts at a bond, and it's ambiguous which side of that bond is going to be doing the attacking. Again, your instructor may not want to use bouncing arrows. That's fine. That's your instructor's choice. But if you want to, send your instructor this video. See if I can change their mind. Tell them to contact me. I'd be happy to talk to them about it. Hopefully that these bouncing arrows that I'll use in my videos will make the concepts more clear to you.
Thanks for watching. The best way you can support this channel is to let your friends know about these videos, especially ones who go to different schools. Help spread the word around the country. As always, don't forget to like and subscribe.